So for the first one, I can say that this implies that x squared plus 7x is equal to 18. If I just take both sides to the 10th power, since they're the same base, I can just set the insides of the logs equal to each other. So I get x squared plus 7x minus 18 equals 0. And I can factor that. So x is equal to negative 9 and 2. But then you have to remember that if x is negative 9, let's see, negative 9 squared is 81 minus 7 times 9. Okay, so that gives me something positive. So you just have to check, in other words, you have to check if I plug in negative 9 for x here and here, do I get something negative or positive inside of that log? Here I tried plugging in negative 9 and I got something positive, so that's actually fine. And then when I plug in 2, I'm clearly going to get something positive. So we keep both of these as answers, but if I were to plug that in and get something negative, say, then that would mean I'd have to throw out one of those answers. So sometimes you have to throw one out. Okay, what about this one? So what I can do is I can add the log base 4 to the other side. So I get log base 4 of x plus log base 4 of x minus 6 is equal to 2. And then I can combine those logs. Log base 4 of x squared minus 6x. So I multiply the inside parts equals 2. And then I can rewrite this in exponential form. So I have that 4 squared is equal to x squared minus 6x. So base 4 to the second power is equal to x squared minus 6x. Then I can add that over. 0 equals x squared minus 6x plus 16. Sorry, minus 16. What's that minus? And then let's see if I can factor that to maybe 8 and 2. So this means x equal 8 and negative 2. And again, here you need to take these values and plug them in for x here. And so I can see that if x is negative 2, I get negative values inside of those logs, and so I have to throw out the negative 2. So the only answer that I have is the 8. Okay, next one. The population of Texas was 21 million. And in 2010, the population was 25.2 million. Write a function of that form. Round k to 5 decimal places. Okay. So what we can say is that in 2010, the population was 25.2 million. So we'll put 25.2 is equal to our initial population, which was 21, e to the k times 10 years time passed. Okay. So I can do that to solve for the k. So I can divide both sides by 21, first of all. 25.2 divided by 21 gives us 1.2. And then I can take the natural log of both sides. So the natural log of 1.2 is equal to the natural log of e to the 10k. And so by one of my properties of logs, that right-hand side just reduces to 10k. And then I can divide by 10. So k equals natural log of 1.2 divided by 10, which is approximately how many decimal places? 5. So 0.01823. Okay, so there's my k. So I haven't quite done what I was asked to yet. First, what I was asked to do is find P of t is equal to P naught, which is 21, e to the 0.01823 t. So that's my answer to part A. For part B, I want to predict the population in 2020, so I'm just going to plug in t equals 20. And when I plug that into my calculator, 21 e to the 0.01823 times 20. I get 26.85, round to 1 decimal places, so 26.9. Okay, then use the function in part A to determine the year during which the population will reach 40 million if this trend continues. So we'll say 40 equals 21. So this is B, this is A, this is C. 21e to the 0.01823 t. So I just need to solve for t. So let's divide by the 21 first. 40 divided by 21 is some decimal. I want to round to the nearest, the year during which. Okay, so let's just do 1.9047. Equals e to the 0.01823 t. Then I can take the natural log of both sides. And divide by that. So natural log of 1.947 divided by 0.01823. Oh. Okay, so if I do t equals natural log of 1.9047 0.01823. So I get 35.34. So in the year 2035. Use that function to determine the age of an artifact that has 38% of its carbon-14 remaining. Okay, so there's my function. So if it has 38% remaining, let's say, so Q naught goes here, and then 0.3, oh sorry, so in other words, it's going to be 0.38 of Q naught. So 0.38 of Q naught is equal to Q naught e to the negative 0.000121 t. Okay, so I can divide both sides by Q naught. And take the natural log of both sides. Divide by that rate. So natural log of 0.38 divided by negative 0.000121. So I got 7, round to the nearest year, 7996.5, so 7997 years. So 7,997 years old. The number of computers infected by a computer virus can be approximated by that. Determine the number of computers initially affected. Okay, so the number initially affected, that would be the number affected when t is 0. So n of 0 is equal to 2.4 over 1 plus 15e to the 0. So 2.4 over 16. .15. What are the units of n? In millions. So 0.15 million computers. How many computers were infected after 6 months? So what is t measured in? Months? Okay, So we're going to plug in 6. Okay, so I'll put all that in my calculator. Now you have to remember parentheses around this guy and parentheses around the whole bottom. 1 plus 15 e to the 0.72 times 6. Oh, negative 0.72. Negative 0.72 times 6. Okay, so I got 2.0008. Round to the nearest 100,000. So tens, hundreds, thousands, 10,000s, 100,000s. So 8, 4. Round to the nearest 100,000. Okay, so 2.00084 million computers. Okay, next one. What is the limiting value of the number of computers infected according to this model? Okay, so if we plug in really big values of t, so let's try like t equal 1,000 or something like that, and see what we get. N of 1,000 months, that's a really long time. So if I plug in like 1,000, I get basically 2.4. So yeah, so you could just plug in really large numbers of t and get that limiting value. So you get 2.4 million computers. The amount of sunlight in Langley's, weird, I've never heard of that unit, okay, is measured for 6 different depths in Lake Lyndon B. Johnson in Texas. Okay, so use a graphing calculator to find exponential regression. Okay, so I entered in all the data, I put it into my exponential regression, and it's saying y equals 399, whoops. 399.71 times 0.74 to the x. Okay, then it says given an is that, find a 12. So we're just plugging in 12 for n. So a 12 is going to be 2 to the 12 minus 1. So that's 4096 minus 1, which is 495. Evaluate that expression. So what is 12 factorial? Well, 12 factorial is 12 times 10 times 9 times 8 times 7. Oh, whoops, I missed 11. You go all the way down. So let's see. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. And then 4 factorial is 4, 3, 2, 1. So one thing you might notice is that this and that are the same. So if we put 8 over 8, 7 over 7, 6 over 6, those all make 1. Okay? And then, so I can reduce it down to that. And then I have 4 times 3 times 2 times 1. So I can divide this 3 times 2, or so 4 times 3 makes 12. Right? So maybe I'll do those in the same color. 4 times 3 makes a 12. And then I have basically 11 times 10 times 9 over 2. So I can, so what's left? I'm left with 11 times 10 times 9 all over 2. And so I can get that 2 out of that 10 there. And I'm left with a 5 there. So I have 11 times 5 times 9. So that's 495. Okay. Use the summation capabilities on your calculator to find the sum. So this is something that you learned to do in class, so I am typing all of that in. Well, actually, let's talk about what this means, really. So if we start, we're going to start by plugging in n equals 3. So I'll get negative 1 to the 3 minus 1, 2 times 3, plus the next one I'll have a 4. Negative 1 to the 4 minus 1, 2 times 4, plus negative 1 to the 5 minus 1 times 2 times 5, and so on. And then I'll stop when I get to n equal 20. So negative 1 to the 20 minus 1 times 2 times 20. So in other words, I'm adding up, let's see, 3 minus 1 is 2. So I have a positive 6 minus 8 plus 10 minus 12 plus, and I keep going like that until I get to minus 40, and so on. So I'll have all these numbers in there. So the one before the 40 will be 38, and it'll be a plus, and so I go on like that. And so I want to add that all up. And if you add all that up, you can use your calculator to do it. But anyway, I want to talk about what that sum meant. The calculator says sum of all of that is negative 18.